As we have been finding limits of functions and graphing functions, we've often found that there's a vertical asymptote. Well, today we're specifically and more formally going to deal with vertical asymptotes. So at the end of this lesson, you'll be able to find the vertical asymptote or asymptotes of a function. Right, what exactly is a vertical asymptote? If f of x approaches infinity or negative infinity, as x approaches a certain value c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. And the biggest thing is that vertical asymptotes occur at non-removable discontinuities. So usually I will look for if it approaches infinity and negative infinity if I'm graphing, or I will look for, if I'm doing it analytically, I'll look for non-removable discontinuities. So let's look at a couple examples. Right, on this one, when it asks me to find the vertical asymptotes, I'm going to do it both ways. I'm going to use it using my graphing calculator, and then I'm going to use it without using my graphing calculator. Okay, if I went to my graphing calculator in this one, I'm just going to save some time for us on this one. The graph of 1 over x looks like this. Okay, so when it asks me to find if there are any vertical asymptotes, I notice that something's happening at x equals 0. I notice that as I'm headed in from the left, I'm headed towards negative infinity, and as I'm headed towards the right, I'm headed towards positive infinity. So as long as I have a limit of infinity at some x value, then that would be where a vertical asymptote occurs. So notice that would be at x equals 0. That would be a vertical asymptote. Okay, if I was not going to use my calculator, I'd be looking at the function 1 over x and looking, is there anywhere that would make, that x would make this function undefined? And I can notice since x is in the denominator, at x equals 0, the function is undefined, and that would be a non-removable discontinuity because there's nothing to cancel out with it in the numerator. So since x equals 0 is a non-removable discontinuity, there is a vertical asymptote, and that vertical asymptote is the line x equals 0. Okay, let's look at the next example. We have f of x equals x plus 2 over x squared minus 3x minus 10. Again, I'm going to look at it from both perspectives. The first thing, if you were to graph this, you would get something that looked something like this. Okay, and you'll notice as I'm approaching 5 from the left, as I'm headed in from the left, I'm headed towards negative infinity. And as I'm headed towards the right, I'm headed towards positive infinity. And as long as one of my limits is positive or negative infinity, then the x value that that occurs at is a horizontal asymptote. So x equals 5 is a horizontal asymptote. All right, looking at it analytically without using my calculator, let's look for discontinuities. I know discontinuities occur where the denominator equals 0. So where does that denominator equal 0? Let's go ahead and factor it. That would factor as x minus 5, x plus 2. So I know there are discontinuities happening at x equals 5 and x equals negative 2. So now if I just rewrite that fraction, excuse me, rewriting the fraction, I notice that x plus 2, so the discontinuity of negative 2, can cancel out, so it's removable. But I do notice that x equals 5 is a non-removable discontinuity, and since it's a non-removable discontinuity, we have the vertical asymptote, which is the line x equals 5. So in either case, we get the same answer. It just depends on, are you allowed to use your calculator or are you not allowed to use your calculator? So now you should hopefully be able to find the vertical asymptote of a function.